today's tutorial is quite straightforward. So before I go into that, I think I'm going to give you some feedback about your tutorial that you have done previously. So most of the issue that I find is that it's not so much about the subject itself, it's your vector. A lot of you doesn't know direction of your vector. So let's go back to simple vector. So let's do it on a two-dimensional. Okay, so if I have 2 points, A and B, let's say this is 3. So this point here will be 1, 3. Okay, let's make it. So this will be 4, 1. So these are called position vector with reference to the origins, X and Y. Okay, so if you want to find the vector between A and B, so it matters which way the vector go, whether it's go from A to B or B to A. Okay, so if I want a vector from A to B, so this is my vector AB. So meaning that it's origin from A going to B. Okay, so to find this vector, you can take many paths because it's a vector. But one of the easiest paths to take is through the position vector that we have. So I can go like that, and then get to B. Okay, so there's one way to go to B. You can go this way, this way, this way, this way, go back to B. That is still the same thing because it's a vector. Okay, so I can take this vector here, plus this vector, plus this vector, and plus. So I can plus this vector, this, and this is still going to give me my vector AB. Okay, so it doesn't matter which path you take. So the easiest path to take is through the vector path of the position vector. Okay, so from A, I want to go to B. So I can only go from A to B. It's going from A back to the origin, and then from the origin to B. Okay, so my vector AB has to be equals to my vector A to the origins plus from my origins to B. Okay, so that is the only way I can get, not the only way, there's one way I can get from A to B. My position vector here is my vector 1, 3. Okay, but I want to take the path from A to O, not O to A. So my vector A to O is a negative of my vector O to A, and that will be minus 1, 3. Okay, so therefore this is equals to minus OA plus OB. Okay, so that is how you work out the vector between A and B. If I reverse it, I want to vector B to A, then it has to go from B to O plus O to A. So in terms of position vector, this will be minus OB plus OA. Okay, so to complete this, this will be minus my 1, 3 plus my 4, 1. And this will be minus my 4, 1 plus 1, 3. Okay, so this is the common mistake that I found in the tutorial that those who are submitted, that you get the which minus which. Quite often people get it wrong, and you end up with a negative vector that what you intend to have. Okay, so this is a simple explanation. So this is in 2-dimensional. So if it's 3-dimensional, you just add the z components into it. As simple as that. Okay, so if you get this right, then the rest you shouldn't be any problem. You have no. I don't find anyone have problem calculating electric field. I don't see anyone have problem calculating the force, Coulomb's law, but the biggest problem arises in the vector itself. The other one is on the question part B. So I give you the first one to calculate the electric field, and then the second one to calculate the force. I think most of you go back to Coulomb's law. You start from Coulomb's law again. So if you're given Q1, and then you have solved the electric field at some point here, P. Okay, and then the next question, I said that I put a charge Q2 here at P. Then my force at this point here is, if I call this my force F2, is simply equals to Q2 times the electric field that I have calculated earlier due to the charge, Q1. Okay, so you don't have to go back to Coulomb's law to calculate the force because you already know the electric field at that point. So all you did is to multiply by the charge that's sitting at that point that you're trying to work out the force. The other one, the other issue is the Coulomb's law itself in terms of vector. Okay, so this is one, and that is on the vector. So the other one is Coulomb's law. So Coulomb's law always defined, so I have Q1, Q2. Okay, so I have 1 and 2. We always define the directions from 1 pointing to 2. Okay, but it's not wrong to do it the other way around as long as you know what you're doing. You have to be consistent. Okay, so I'll define this force as F2 and this force. So the two forces that you're going to define is going to be away from each other. F1. Okay, so associate to this R, you have a unit vector. So you can see that in this vector, so I can see that this unit vector R is pointing in the same direction of F2. Okay, that's what we define it to be. So we define our F2 to be in the same direction of R, of the vector R. And we define F1 to be in the opposite direction of R. So when we write the equations, my F2 vector has to be equals to Q1, Q2, that's my Coulomb's law, 4 pi epsilon naught R squared, AR. Okay, so note that this and this is the same direction. And then we define this to be equals to minus F1, because F1 is in the opposite direction. Okay, so you can define the R vector to point from 2 to 1. It's just that you need to be consistent. You need to know the unit vector R then will be same as F1. You get what I mean? So if I define it the opposite directions, if I define my R, you can do that. My vector R, now my unit vector is here. If I put this Q1, Q2, now you see that the unit vector is the same direction of F1. And then it will be in the opposite direction of F2. So in this case here, let me clean up a bit of my slide. In this case now, you can see that if I define it this way, my F1 is the one that is in the same direction of AR, my unit vector R. So when I write my equation, this has to be equals to F1 equals to, this is still the same, Q1, Q2 over 4 pi epsilon naught R squared times the unit vector R, because they are in the same directions. So if I define it this way, then my F1 will be in the same direction of my unit vector R. And now I'm going to be equals to minus F2. This is also correct. Okay, because my AR here is the negative of my AR here. So if I put in, if I change my AR, let's say I call this AX. Okay, my AX is equals to minus AR. Yeah, because they are in the opposite direction. So if I put that in, then the equation will get back to this equation. So it has, as long as you get the vector direction correct, then these equations will sort itself out. Okay, that depends on where you define the direction of R. But you have to make sure that the arrow of that two vector pointing same direction, it has the same polarity, meaning that if they're pointing the same direction, they're both positive in that direction. Opposite will be negative. Okay, so if you get that right, then you shouldn't have any problems. And with these equations, if my charge has a negative sign, if I put a negative sign into it, the vector will automatically change directions. Okay, so what it tells you is that if both charge is the same polarity, then the force will be in the direction as I define it. If one of them is negative, then if I put it into these equations, then my vector will become a negative AR. Then you see that the force will automatically go in the opposite direction as you define it, and it become an attractive force. Okay, so that is Coulomb's law in vector. So if you get that right, and you get this vector thing here, position vector right, then you shouldn't have problem solving Coulomb's law or electric field. Okay, so that is just the feedback I wanted to share with you based on what I have seen in your submissions of your tutorial questions. Okay, is that clear? Everyone understand that? Still have difficulty? If you don't sort this out, then you continue to have difficulty understanding the vector, which is the very basic of this module, because if you don't get your direction right, then you always find the force in the wrong directions, or you find the electric field in the wrong direction as you expect it to be. Okay, so make sure that you understand, you really understand how to calculate position vector. So with that, if no questions, we're going to move on to today's tutorial. So we talk about electric flux density. So this is just a very simple tutorial, just to get your mind around the two boundary conditions when you have different medium. When the electric field shows up on a different boundary. So give that a try. Then maybe 10-15 minutes on that. Okay, summarize the questions. So let's say this is A, and this is the electric materials. It has an epsilon R equals to 6. And then we applied the field parallel. So a few things you need to know. You need to know how the field behave at a parallel boundary, whether E is the same or D is the same. The next you need to know is the relationship between D and E, and D with E and P. So which one? EA equals to E, or is it DA equals to D? One or two? Okay, everyone agree it's one. Okay, so what's the relationship between D and E? Okay, we know that dA is equals to D. So what is dA? What's the relationship? Something here. E epsilon R epsilon naught. What is epsilon R? Is it 6? This is the applied field. It's in the air. So what's ER? Epsilon R. Okay, epsilon R is 1. But we don't really need this actually, because we don't really need this. We already said that EA is equals to A. So we already find E is equals to EA is equals to 100 watts per meter. Okay, so based on this relationship, D equals to epsilon R epsilon naught, we can find what is D. So we know that this is equals to 100. This is equals to 6. This is equals to 8.854 times 10 minus 12. Okay, so E is equals to 100 watts per meter. D is equals to epsilon R epsilon naught E. That will be equals to 6 times 8.854 times 10 to the minus 12 times 10 times 100. That give you 5.31 times 10 to the minus 9. That would be 5.31 nanocoulombs. What's the units? Per meter squared. Polarization P. So we know that epsilon R is equals to chi plus 1 or x plus 1. So D is equals to and this is our polarization. So P will be equals to D minus epsilon naught E. So this is equals to 5.31 times 10 minus 9 minus 8.854 times 10 minus 12 times 100. And let's give you 4.43 times 10 minus 9. Units is the same, isn't it? Nanocoulombs per meter squared. Okay, you can see that why they are the same, because epsilon r doesn't has a unit. Okay, we have epsilon naught times the electric field. Here, my polarization against this parameter x here doesn't has a unit. It's also epsilon naught times the electric field. So they are of the same units. Okay with that? Can I move on? Everyone got that? The next one. Similar example, but the field now is in a different directions to the boundary. So what's the same now? Okay, D is the same. So dA is equals to D inside the dielectric. So what's dA? So D relationship is epsilon R epsilon naught times the electric field. But EA applied field is in the A. So epsilon R is equals to 1. Okay, so dA is equals to epsilon naught times EA. And that's equals to D. So D also equals to epsilon naught times EA. But D is equals to epsilon r, epsilon naught E. Okay, so if I write out this whole equation, dA is equals to D is equals to epsilon naught EA is equals to epsilon r, epsilon naught E. So from this equation, you can find out what is D, you can find out what is E. And you know what is D, you know what is E, you can find the polarization. So D is simply equals to epsilon naught times EA. That will be 8.854 times 10 minus 12 times 100. And that will be 8.854 times 10 minus 10. That will be 0.885 nanocoulombs per meter squared. From this equation, I can work out what is E. So E will be equals to EA divided by epsilon R. 100 divided by 6. So we know what is D, we know what is E in the dielectrics. We can work out the polarizations. Okay, so the polarization is equal to 0.742 nanocoulombs per meter square. Okay, any questions? Okay, no question? Understand? Yes. 895. 0.885. Is it? Got there right? 0.885. Right?